I would like to welcome you to the presentation of Batch 9's Digital Assignment 3 for the course BECE204P, Microprocessors and Microcontrollers Theory. The title of our project is Swept Frequency Capacitive Sensing with Arduino. The members of the team include Christo, myself, Suseel, and Surya. The contents of this presentation are: first, we will start off with the theory of our project, understanding what capacitor touch is, and understanding how our idea brings on a new frontier to the existing technology of capacitive touch. Moving on, we'll be looking at hardware. The hardware used in this project, how they impact the project, what are their roles and the purpose in this project. Moving on, we will look at the software that is used to bring life to the project, the Arduino code and the Python software implementations, how they work, and their impact on the whole project. Finally, we will end off with a demonstration video of the software and the hardware at work. So, what is the aim of our project? Our project aims to present a novel method of interacting with everyday objects around us. Using a technology called Swept Frequency Capacitive Sensing, we can not only distinguish between a touch event and a non-touch event, we can also recognize complex and different human interactions, including grasping an object, being near an object, the very presence with an object, and all sort of different human interactions. This will be a huge leap from conventional touch screens and move beyond what was thought possible as materials that can be used for touch sensing. Now let's take a deep dive into the theory of our project and understand what is touch capacitance and the science that makes it all work. So what is capacitance? Capacitance is a electrical property that we have been learning from our elementary school days. It determines the ability of a material to store electric charge in a given electric field by accumulating electric charges on two closed surfaces that are insulated from each other. So we can see over here the construction of a very basic capacitor. It consists of two electrodes separated at a distance d with an area of A. They sandwich a dielectric medium between them. So this capacitor is capable of storing a certain charge that we quantify using capacitance. We can quantify the charge stored in these capacitors using the capacitance formula. The capacitance formula determines the ability of a material to store charge using the three variables, that is, the dielectric constant, the area of the two electrodes, and the distance between them. So, using this formula, we can exploit these three variables to understand if there is any change in the capacitance. We can either change the distance or the dielectric or the area and quickly identify if there is any difference in the capacitance, right? So we are going to use this property of capacitance to construct modern touchscreen displays. So how does capacitance in modern touchscreens actually work? So modern touchscreens essentially consist of a copper pad, which is an electrode over here, protected by a protective overlay, which insulates it from the outside world, and this copper pad is directly connected to a sensor, which is responsible for exciting it by providing a fixed frequency signal and also sensing if there's any feedback from the copper pad. So how does this actually work? So we know that the sensor is responsible. This sensor over here will be first of all excited by a fixed frequency, right? So since the copper pad itself has very minimal, almost negligible capacitance to it, there is no feedback from the copper pad to the changing wave. When a frequently fluctuating wave is applied to the copper pad, there is no feedback or no resistance from the copper pad to this change. However, when a finger which has a larger capacitance due to the virtue of water in it approaches the electric field of the copper pad, we realize that there's a sudden relative increase in the capacitance of the sensor. Therefore, now when a signal is applied to this copper pad, we observe a feedback from the setup. This feedback is recorded by the sensor by the electronic components here that then can determine if a finger has approached it or not. So therefore, by using the simple virtue of capacitance, we are able to quickly and intuitively determine if there is any sort of finger approaching the sensor. So using this technique, although has a short form, by the virtue of its design, it's only capable of detecting whether a finger is present or not, because it only provides feedback when there is a finger approaching the sensor. We do not have any more data to work with. This is a limitation of modern touchscreen. Okay, so now let's look at an alternative approach here, which is called Swept Frequency Capacitive Sensing. What is Swept Frequency Capacitive Sensing? So ideally, in contrast to traditional touch sensing, over here we will apply a range of frequencies. So we will sweep through the frequency range, applying this frequency to the said electrode, and then we will measure the feedback across all of these frequencies. What is the use of doing this? Why do we do this? Because we are able to now get a multitude of range of data from which we can measure and determine what type of touch it is. Also, we understand that when we apply different frequencies, each object, the electrode, behaves differently to touches. An object might show a greater capacitive difference at lower frequencies, while it might not show such a huge difference at higher frequencies. So the frequency response of each electrode is also different. So thereby, using a swept frequency technique over here, we are able to get a range of data points through which we can either use ML techniques or data manipulation techniques to add more context to the touch event that is happening. So now, how do we do this? How do we implement the swept frequency technique? Generally speaking, this is implemented using a wave generator, which is able to generate a clean sine wave. Then this wave is amplified into a sizable difference so the capacitor can work, and then directly applied to the object. Then, when there is a difference or change, when a response wave is recorded from the sensor, it is converted from analog to digital using ADC, and then enveloped to only find the higher ranges, the top of the frequencies, and then analyzed using a microprocessor or a microcontroller. So let's look at an existing implementation. We are not the first to discover swept frequency touch sensing. This implementation has been discovered and tested by various other researchers and scientists. One of the notable implementation is called Touche, and it was published by Disney Research Pittsburgh along with University of Tokyo and Carnegie Mellon University. Over here in this implementation, as we can see, they use Touche, which is basically the brain of the whole processing. Using a digital control, they will ask the wave generator, AD5932, to generate clean sine waves at different frequency. And then this frequency goes through a low pass and high pass filters, and finally is amplified to a sizable difference and applied through an inductor to the object. Now, this object this could be an electrode, it could be a mug as in our case, or it could be a fruit, a carrot, even a human body. And then when this object detects a change, it applies opposing electric field, which then is passed through this isolating buffer, which could be either a diode or so on and so forth. And then it passes through a low pass filter, and then an envelope detector. So the envelope detector converts the rapidly changing response voltage to a more clean gradual wave that can be then analyzed by the Touche. So, as we can see here, the existing implementation is extremely complex and sophisticated, which requires multiple filters and multiple and a wave generator, amplifiers, so on and so forth. We aim to simplify this technique using a much more simpler approach using Arduino and cheaper components that we can buy off the shelf, and try to achieve comparable results. While it will be quite challenging to achieve the resolution and dexterity implemented using dedicated components, we hope to achieve something similar to the results observed here using the simple ATmec 328 chip on the Arduino and using a simple RLC circuit. So now we will look into the hardware implementation, which will be handled by my teammate Surya. So handing it over to him. Thank you.
So thank you, Christo, for explaining the theory of the project. Now let me explain the hardware of the project. So let's now deep dive into the hardware of the project. These are the components required. Arduino, USB cable, resistors of 10 kilo ohm, 1 million ohm, 3.3 kilo ohm. So these are the pictures of the components. 1 million ohm resistor, Arduino, 3.3 kilo ohm, 3.3 kilo ohm resistor, and this is 10 kilo ohm resistor. And these are the other components required. Capacitor of 100 picofarad and 10 nanofarad. This is 100 picofarad capacitor and this is 10 nanofarad capacitor, and inductor of 10 millihenry, and this the inductor, and diode 1N4148 diode. This is a diode, and we have used water bottle as sensing object. But in our case, we have used a cup of water as a sensing object in our experiment. So this is the circuit diagram. If you see here, the ground is connected to pin 5, that is here. And if you see this port number 9, which is pin 22, is called as PBOC1 pin. This is especially used to generate precise PWM waves, PWM waves. So which is internally connected to timers. These precisely generate square waves, but to our concern, we can't use these square waves directly. So we are using this RLC circuit to convert them into similar sine waves, like which are similar to sine waves, so that it would be easy for us to uh, sense the frequencies later. So RLC circuit, which has a resistor of 10 kilo ohm and inductor of 10 millihenry and capacitor of 10 nanofarad, which is sent to object to sense. So in this process, capacitor tries to resist the change. So due to this, some amount of change is brought in voltage, which in turn releases some energy. So this flows in the opposite direction. When this opposite direction flow happens, we bring in this diode so that this diode lets in the opposing flow of opposing flow of voltage or energy, whatever it is. So this goes through this resistor, uh, which is of high resistance, like 1 million ohm. We got a high resistance because sometimes this capacity, the change caused by this capacitance might be very less. So to amplify it or to make it noticeable for the Arduino to pick it up, we bring in this high resistance, which in turn is connected in parallel with this 100 picofarad capacitor. So this capacitor is also called as a filtering capacitor because this filters out the noise or disturbance produced by this opposing flow, and which produces the final analog signal, and which is into this analog port, which is pin number 7 of this Arduino chip. So this is how the circuit diagram works, and this is our hardware setup. If you see, this is our Arduino chip, and this is our breadboard. and this is our USB cable which is connected to the computer, and this is our inductor. This is our 10 nanofarad capacitor. This is our sorry, this is our diode. If you see this, sorry, if you see this part, the small part before our 10 nanofarad capacitor, this is our diode, and this is our another capacitor which is of 100 picofarad, and these are the resistors, and these are the connections. If you see, these are the connections. This is the Arduino. Yeah, that's about it. And these are the shields, pin holders, and the other components which we discussed previously. Um, yeah, that's about it. So I asked Sushil to take over the software part. Yeah, thank you.
So thank you, Surya. I am Suseel Mathusoothanan, register number 21 BCE1645, and I'll be discussing the software part of this project. So let's dive in. So this Arduino code generates a frequency sweep signal using counter 1 and measures the response signal from an analog sensor connected to pin 0 for each frequency point. The code starts with defining some bit manipulation macros that are used later in the code to set, clear, check, and toggle bits in variables. These macros are then used to configure counter 1 for generating the frequency sweep signal on pin 9. The frequency sweep range is defined by the variable n, which sets the number of frequency points. In the setup function, the counter 1 is configured for generating a fast PWM signal with a clock source of IO clock with no prescaling. That is, running the maximum frequency of the microcontroller. The waveform generation mode is set to generate a signal that clears the output on compare match and sets it at the top value. The top value is set to 110 using ICR1 register, which defines the counter top value for the PWM signal. The output compare register OCR1A is set to half the value of the top register, which defines the duty cycle of the PWM signal. After the counter 1 is configured, the main loop function starts. Inside the loop, a for loop sweeps through the frequency range defined by n. At each frequency point, the counter 1 is stopped, the frequency registers are updated with the new frequency values, and the timer and the counter is restarted with the new frequency. The response signal from the analog sensor is then read and filtered using a simple moving average filter. The frequency and response values are stored in frequency and results arrays respectively. Finally, the plot T array function is called to display the frequency sweep response plot on a connected computer. The tog macro is used to toggle pin 8, which can be used as a sync signal for a scope or other equipment. Moving to the next slide. This slide discusses about the Arduino code for sending the data from the microcontroller to the computer. This code includes two functions, send data and plot T array, which are called to send specific types of data. The send data function takes three arguments, command, y value, and x value, which represent the type of command being sent, the y and x values to be sent respectively. The function starts by breaking down the y value and x value into their most significant byte and least significant byte, and sets a 0 byte flag that keeps track of which bytes have 0 value. The function then calculates a checksum value that is the remainder of the sum of all the bytes divided by 255. If the checksum is not equal to 0, the function sends the data over to the serial port by sending a start bit followed by the command. The MSB and LSB of the XY values. If the checksum is not equal to 0, the function sends the data over to the serial port by sending a start bit followed by the command. The MSB and LSB of the Y and X values, the 0 byte and the checksum. The plot T array function takes 3 arguments: CMD, array1 and array2. The CMD argument represents the command type and is used to differentiate between different types of data being sent. The array1 and array2 arguments represent arrays of floating point values that are to be sent over to the serial port. The function first sends a command to the PC to inform it that an array is about to be sent. It then sends the data in arrays by calling the send data function for each values in the arrays. Finally, it sends a confirmation to the PC to indicate that the array has been sent completely. These are the two codes used in the Arduino for sending data and sensing the gestures from the object. Now we'll move on to the Python code to read data. This code defines a function getFromSerial that reads data from a serial port and returns the X and Y axis data as two separate lists. The function takes a serial port object port as its argument, which is of the serial.serial type from the PySerial library. The function returns a tuple of two lists, the X-axis data and Y-axis data respectively. The function reads data from the serial port in a loop until it receives the end of array command. It first reads a single byte from the port and checks if it is equal to 0x00. If it is, it reads the next 7 bytes, which constitute a data packet. The data packet is structured as follows: byte 0, command word, 2 for start array, 3 for end of array, and other values for data packets. Byte 1 to 2, Y-axis data. Byte 3 to 4, X-axis data. Byte 5, 0 byte. Byte 0 to 3 indicate which data bytes are 0. Bit 7 is reserved. Byte 6, checksum. Sum of bytes 0 to 5 modulo 255. The function then passes the data packet and extracts the X-axis and Y-axis data. It also checks the checksum to ensure that the data is valid. If the checksum does not match, the function prints an error message and discards the data packet. If the command word is 2, the function resets the X-axis and Y-axis, lists and sends the... If the command word is 2, the function resets the X-axis and Y-axis lists and sends a flag to indicate that the new array is starting. If the command word is 3 and the flag is set, the function returns the X-axis and Y-axis lists as a tuple. The main section of the code creates a serial port object and calls the getFromSerial function from the port object as an argument. The returned X-axis and Y-axis lists are printed to the console. So this is the software part of this project. Next, Surya will be demonstrating the project.
Okay, so that now we have explored the software side of things. Let's now look at the hardware of this project. So we have the Arduino here, which is responsible for sending out the frequencies and capturing back the responses. And then we have the motherboard, which has a circuit responsible for filtering the waves, smoothing, creating the RL circuit, and then smoothing out the results, right? And then we have the sensor wire here. This can be used, this is currently dipped in the mug so that it is, here the mug will act as a whole sensor. The mug is filled with water so that the whole mug can be used as a sensor here. Since that now we understand the basics, let's first of all fire up the GUI. Okay, the GUI is set up, the GUI is active. We are going to connect the Arduino to the computer. The Arduino is active. Now we will connect the GUI to the port. And yes, we are receiving readings from through the serial of the Arduino. So now, first of all, before we move on, we should register baseline reading so that we know what is the response it should receive when there is no touch interaction. So we go ahead and register the baseline reading. Give it a second, and yes, we can see that the program has drawn a green line showing that what is the prediction or what is the estimated reading for baseline. Now we're going to do a slight finger touch, a small finger touch, and then we're going to register a single finger touch, right? So register, give it a second, and there we go. We can see a new prediction has come as blue line. So if I do a finger touch, we can see the touch detection changes to finger touch, move it, baseline, finger touch, baseline, finger touch, baseline, finger touch. So it's quite responsive. Now we can also register another interaction, which is grip. So let's just go ahead and register grip. So grip, if I hit register grip, give it a second, and now we have a new prediction for grip. So I can remove my hand, it goes back to baseline. I touch finger touch, grip, grip, finger touch, and we can see it's able to quickly differentiate between the different type of interactions that the sensor, or the mug in this case, is having with the finger, just with one wire. Now also I can have a fourth interaction, which is in water. As you can see, I will register in water, and it's in water. It's able to detect that it's in water. I touch it, finger touch, grip, in water. I can do it in any order, and it should be able to detect and differentiate between all of them. And using this UI, I can reset all the actions. Even if I want, let's say I want to add another action, like touching the handle of the mug. So as a handle, mug handle, mug, mug handle, and I probably want the graph color to be white for this sake. I'm going to add this action. The GUI is updated correspondingly. So first of all, once again, I'll register the baseline. And I will register now the mug handle. So even without just touching the edge of the mug, we are able to see some differences in the frequencies. And there we go. We can see the mug handle, baseline, mug handle, baseline, mug handle, baseline. And this can be differentiated with something like a grip. So register grip. So there is grip, there is mug handle, so on and so forth. And just like that, we are able to differentiate between different touches using a single wire and an Arduino. Thank you. Have a good day.
Conclusions and references. The conclusion. The proposed Swept Frequency Capacitive Sensing technique is a significant breakthrough in touch interaction technology that can greatly enhance the user experience in a variety of applications. The ability to detect and recognize complex configurations of human hands and body provides contextual information that can greatly expand the range of possibilities for touch interaction beyond traditional touch screens. This novel technique has the potential to revolutionize the way we interact with technology and create new opportunities for innovation in various fields. So this is the main conclusion. Now references. This is a website and this is a research paper. I can show you them. This is a website which we refer, and this is a research paper. So yeah. So that's it from our side. Thank you so much. I thank Satish sir for giving us this opportunity, for giving us an opportunity to learn. Thank you so much.